Alright, let's now move beyond analysis using physical experiments, but let me remind you very quickly what we discussed just earlier. So we spoke about the 3 disadvantages of using experimental analysis. So you have to fully implement the algorithm, which may not be worth the time. And also you have to make sure the comparison environments you have set up must be identical among the algorithms. So you have some fair comparison. And mostly, it may not be so easy for you to actually spend the time setting up all the scenarios in order for you to really draw some conclusive claim about the which algorithm is actually more efficient. So these are the 3 disadvantages of using physical experiments. Please make sure you understand them before you move on with the current part of the lecture. All right, let's now try to move beyond. So what will be a better approach? So we want to have a better approach to analyzing the efficiency, specifically running time. That'll be the focus for this course. Of algorithm, there should be 3 things. Number 1, it should allow us to calculate the relative efficiency. So here, I'm going to explain a little bit more about relative efficiency later. But you can think about relative efficiency as opposed to absolute one, meaning that we don't really have to measure the exact milliseconds that has elapsed between the algorithm execution. We don't have to. Instead, we're just going to look at the skeleton or the sketch of the algorithm, and then we will be able to calculate the relative running time. We'll see. And most importantly, we are doing relative efficiency because we want to be independent of the hardware and software environments. That's what we really want to do. So meaning that once you get a relative efficiency among the different candidates' algorithms, you will be able to extrapolate that either running them on Mac or running them on Unix, running them on Linux or running them on Windows, you're going to have the same relative performance. So that will be the key to really keep in mind. Right, number 2. The approach can be applied using a high-level description, meaning that when I say high-level description, meaning that we can be slightly more tolerant on writing the exact details for the code, but we still want to be as detailed as possible. Think about the following scenario. Let's say you go through some job interview, and your potential employer, they simply gave you some programming problem to solve. And they ask you to program your solution on a whiteboard. Apparently, you don't really have the Eclipse or IntelliJ to really tell you the exact compilation errors you might run into. But in that case, even that, you still don't really want to write some ridiculous code that simply wouldn't even compile in the first place, right? You want to be as precise as possible. But sometimes, if applicable, some mistakes for compilation can be tolerated. We'll actually see more examples as we go on. But in the lectures, I'll try to give you the code fragment of Java in the subsequent modules as precise as possible. Of course, it will be up to you to really type them out into Eclipse and then try them out. Okay. Let's see the last bullet points here. And most importantly, the better approach should be able to consider all the possible inputs. Theoretically speaking, it's difficult or if sometimes even infeasible to really consider all the possible test inputs because they are simply unbounded. That we wouldn't really cover testing strategy in this course. If you're interested, you can definitely study maybe some advanced level software testing course in the 4th year. But anyway, we'll cover some techniques whenever applicable, but we wouldn't really have a dedicated lecture for that. But most importantly, you want to keep in mind, especially we want to consider the worst case scenario. Every time you want to make a claim about how efficient your algorithm might be, you want to make sure you really base your claim on how your algorithm can perform in the worst case scenario. Otherwise, if you only report its performance in the best case scenario, it's not very representative, for example, right? All right. And we will learn a better approach that contains 3 ingredients. So after knowing what we are supposed to do in the better approach, let's see exactly what it should look like. So number 1, we want to know how to count primitive operations. In the next slides, I'm gonna define what a primitive operation is, and we're gonna go through examples to actually practice. Number 2, we want the approach is going to approximate the running time as a function, mathematical function of input size. So we may have a constant function, linear function, quadratic function, all the way to exponential function, right? So that's something we'll actually see. And number 3, the approach is going to focus on the worst case inputs. So every time you want to claim the running time for your algorithm, you want to make sure that one really represents the running time for the worst case, not the best case. Best case scenario is not very meaningful for us. All right. Having outlined the better approach, how it should look like, let's now go over what a primitive operation is, and we're going to see some example. Let's see how we can count the number of primitive operation, and the count must be precise as we do the exercise together. So what's really a primitive operation? A primitive operation is basically some atomic units that cannot be decomposed any further. Corresponds to a low-level instruction with a constant execution time. You can think about, for those of you who might have been taking 2021, or you might be taking 2021, the computer organization course. So every instruction for a particular CPU is called a primitive operation. Of course, we don't really go down to that low level, but at least for as far as Java programming is concerned, for every simple line of code, we call that a primitive operation. It's just an analogy. You can think about what you learned in 2021 as the CPU instruction. That's like a primitive operation, which will take almost no time, or very small amount of time to really complete the operation execution. Let's go over the list of primitive operation. So variable assignment is considered as a primitive operation. So for example, whenever you see something like x is assigned to 5, that's considered as a primitive operation. That will simply take a constant execution time. When I say constant execution time, it simply just vary between platform to platform. Maybe you're using a particular type of CPU, it might take maybe a faster like a shorter amount of time to complete a particular primitive operation. But for another CPU, it might be slightly faster or maybe slightly slower. But the difference is not so important for us. It's negligible. So all we want to focus on would be the relative performance, like a relative number of primitive operation that will take for your entire algorithm to really execute. That's something we will conclude as well. But I just want to give you some look ahead. So variable assignments is definitely a primitive operation. It's just do it, and then you'll be some constant amount of time, like a constant, like a primitive units of time. And if you want to index into an array, let's say you give it an array A, and you want to go to index I. So we are making the assumption that I is a valid index. And also, when you perform any of the arithmetic, relational or logical operation in Java or in any other programming language is also considered as primitive. For example, this is arithmetic, plus, minus, multiply, divide, and also modulo, right? The percentage sign. And this is the relational operation larger than, less than, larger than or equal to, less than or equal to, and also equals. And this will be the logical operation, right? The negation, the exclamation mark, the band, and also ampersand for conjunction, vertical bar for disjunction, right? That's all you learned in the earlier foundational course in Java. So these are all considered as primitive operations. And if you want to access an attributes of some objects, it would also be considered as a primitive operation taking constant time. Let's take one example. Let's talk about ACC.balance, right? It's also nice for you to review about what the dot notation really means in OOP, object-oriented programming. Let's now switch to the notes and let's talk about this attribute access specifically. So what we're talking about is a constant primitive operation. So primitive operation. And every primitive operation will take constant time to execute. And specifically, let's now talk about attribute access. This is simply just one example of primitive operation. And the example we got is ACC.balance. Okay, let's do some anatomy of the dot notation, shall we? So you can think, as you learned before, ACC over here is so-called context objects for you to invoke either attributes or method. So this is the context objects. And of course, in order for this particular dot notation to be valid, ACC must be declared with some relevant type. So let's make the following assumption. So let's say earlier in the code, we actually declare account, assuming that account class actually exists, and also ACC, right? So that's the declaration. And balance is simply some attributes that was declared in the account class, right? That's something you can assume. Okay, and now it's really important for you to recall what exactly will the dot notation really do. Okay, basically the dot notation is going to involve the following. It's going to look up the address that is stored in reference variable ACC, right? So what we learned before in the Java course, the earlier Java courses, was there are two types in Java. Either primitive type, like a integer, boolean, double, float, and also character. But all others will be considered as reference type. So account over here is so-called reference type. Basically, any class that you can see from the Java API library, like array list, linked list, string, and etc., or any class that you declare on your own. In that case, both kinds of classes will be considered as the reference type. Okay. And now every variable that's declared as the reference type is going to store the reference or address of some objects. So what's going to happen in this case is going to be like this. So ACC, diagrammatically, is going to point to somewhere in the memory, right? So that's how we visualize an object over here. And the object is of type account. And we are making the assumption that one of the attributes that's declared for every account object is a balance. So let's put balance over here. Okay, that's the attribute name. And then there might be some value over here. For example, it could be 100, just for now, right? What is the dot notation going to do is as follows. We're going to look up the address that is stored in the reference variable, right? So we're going to, what's the address that's stored in ACC? That one indirectly actually points to this particular memory location over here. So this particular lookup notation, this particular lookup operation over here takes only constant time. It's not really, it's not considered as an expensive operation, right? So that's really important to really highlight this. So this part over here is really the dot notation. This is really the dot. And this is a constant time operation. And whenever we talk about constant time, what we really meant to be a little bit more informal is a cheap operation as opposed to expensive. Okay. And finally, up to this point over here, after the dot, we actually already look up the location of the memory for that particular object, ACC, and then we want to get access to its balance. In that case, we just want to get to balance. That's also constant time operation. Okay. All right. So there's a very detailed walkthrough about how you can understand like a dot notation for accessing the attributes of some reference variable is really a constant time operation, which involves about looking up the address in the that is stored in the variable, and then go to that particular memory location and go to that particular attributes. So these are the two mini steps, but to sum them up, it's gonna be a constant time operation. All right, hopefully that makes sense to you. You might be wondering, what about method call? If you simply just try to do like an attribute access is simply constant. Oh, by the way, just to mention, if you only try to do dot notation for access attribute access, you may say ACC does something and then does something, does another attribute, and other attributes. It doesn't matter how many attributes you're trying to access, like how deep the nested level is. In that case, it will still be considered as a constant time operation. Okay, let me just write it down, which is really important. In general, you may have to access an attributes using multiple dots. Okay, multiple dots syntactically. Okay, for example, you may have to say obj, some object reference, and then dot attribute 1, dot attribute 2, dot attribute 3, all the way to dot attribute n, right? You may have as many as possible, but we still consider even this in general will still be considered as a constant time operation, right? Eventually, we just want to access this particular attribute an, so it will still be considered as a constant time operation. Constant time primitive operation. Okay, just to make it more general for you. So now the follow-up question is, what about method call, right? So method call is fundamentally different from attribute access. When you try to get access to an attribute, it's only this particular single field that you're trying to get access to. But what about calling a method? For example, if you say acc dot method n, and then just simply that, can you actually say whether it's going to be a cheap or expensive operation? More precisely, can you actually say whether or not it's a primitive constant time operation or otherwise? You cannot say that in general, to be honest with you. But why? You can think about it, but we'll definitely get there. Let's switch back to the slides. Right, so if you want to return from the method, in that case, it's only a return statement. It's simply just returning the value back to whoever the caller is for the current method. So that's also considered as a constant time operation, primitive operation. So whenever I say primitive operation, sometimes I might just interchangeably use constant time operation. Just hopefully you can catch that. Right, so this is the question I just asked you a few seconds ago. Why is a method call in general not a primitive operation? Sometimes it might be, sometimes it may be not. So why? You can think about it by pausing the video. All right, assuming that you thought about it, the argument is very simple. Because you simply don't know which method you're calling. If the method itself contains only a single line of code, in that case, the method call itself should be very cheap, should be a primitive operation. On the other hand, if the method itself contains very sophisticated, let's say loops or if conditional, in that case, it may actually go beyond primitive, right? So it may be a call to a cheap method, in which case, for example, just printing hello world. Or an expensive method, in that case, maybe the method itself will do something that's beyond primitive, right? That's something you will definitely see later. But let me just conceptually, let me draw the idea for you, okay? So when you're trying to make a method call, there are two cases. Okay, case number one. Okay, let's make it very conceptual. Objects dot some m. Let's say it doesn't take any arguments, right? So now if I simply ask you over here, obj.m, should it be considered as a primitive operation? So your answer should be yes or no. It depends, right? Case number one. In the case where, conceptually, let's say this is the definition for m, right? Let's say the definition for m is a void method, but of course you can also return something if you like, but just as a conceptual sketch. If every line of code over here it's just a primitive operation, in that case, adding up primitive operations will just be another primitive operation. Okay. In that case, all primitive operation. In that case, case number one, it will be a primitive operation. Okay, what about case number two? And for case number two, let's say here we have the definition for the same method m. Typically, as if your method involves a loop, you have to watch out for the complexity, right? So for example, you might say for maybe integer I, and maybe I is strictly less than maybe some array, a dot, maybe length, and then I plus plus, right? In that case, you might do something inside the loop. I'm not saying that whenever you have a loop, that means you cannot make your method primitive operation primitive operation anymore, but you have to watch out. We'll definitely see more example as we go. I'm just saying that in case number 2, in this case, since now the method itself involves another block of code over here, and that the performance of that particular loop depends on the length of the array. So now can the length of A can be very small or it can be very large. It depends. When the length of A gets very large, in that case, n the performance of n cannot be considered as a primitive operations performance anymore. So that will be the idea. Okay, so just one example. So for case number 2 is non-primitive operation. Okay, so these are the 2 cases you want to watch out for. Okay, all right, let's now move back. Oh, of course, let me say one more thing, which I really meant to say. It's also possible that inside the method, you just want to call another method. Maybe you want to call another method m2. So now whether or not n is primitive also depends on whether or not m2 is also primitive. You want to make sure in order for a method to be primitive operation, every line of code, including just another method call, must be considered as primitive operation. If any one of them is actually complicated enough to be beyond primitive operation, this method here is not primitive operation anymore. Okay, hopefully that's intuitive. All right, let's now consider the first example of counting the primitive operation. Before that, I would suggest you actually review about the definition, this list of the kinds of primitive operations before you move on to this example.